Welcome back. Now we are solving the final question we had for k-means, which is how good is this algorithm we just developed, called Lloyd's algorithm, which solves these subproblems. So what we would like to do, for example, or what would be nice to have, is if we could also characterize the global minimizers of k-means, like we did it for the rank or matrix factorization problem with truncated SVD. Well, unfortunately, this is not possible here for k-means, or at least so far nobody has come up with a solution. So for k-means we have this problem that we get a solution which is a local minimum of our objective, but we don't know how close it is actually to the global minimum. So in this respect we cannot say much. But we can characterize the global minimizers of the k-means objective when we fix one of the factor matrices. So what we do now is we compute the minimum of our objective when we fix either y or x. And the one result for fixing y is that the centroids are actually the solution to the objective. So that means that given my data matrix D and the cluster assignment matrix Y, the minimizer of the optimization problem, which is to minimize the residual sum of squares of my matrix D and the approximating low rank product for a matrix which is real valued, that the global minimum of this objective is given by the centroid matrix as we have defined it. And the proof is actually not too complicated. So first of all, we show that the objective in equation 2 is convex. This can be done similar to the way we showed that the residual sum of squares for regression is a convex problem. And then if we know that this objective is convex and it is also smooth, right, because x is real valued and the residual sum of squares is a smooth function itself, then the minimizer is given by the stationary points, as we have discussed also for regression. So then what we do is we apply func, and then we compute the gradient, which we have derived already in the optimization lecture. So if you want to look that up, have a look there. And then if we compute here which points satisfy this constraint, then we see that x has to have this form of the centroids. So centroids are actually the solution if we have given a cluster assignment matrix. Nice. So how does it go the other way around? Now if we fix the centroid, so given our data matrix and the centroid matrix, then the minimizer of the optimization problem to minimize the residual sum of squares, subject to y is in the set of all cluster indicator matrices, is the matrix which assigns every point to its nearest centroid. Well, this is actually quite cool because we can here denote the global minimum of this highly discrete optimization problem, right? I mean, we have here this problem that y is an indicator matrix, so it's binary, and that makes the optimization problem discrete. And herefore we have also not any gradients, but still we can denote the global minimum of this objective, and this is really cool, and this is one of the reasons why most clustering algorithms actually rely on k-means, where you can denote here for this highly discrete subproblem the solutions. Okay, and how can we prove that? Well, it's actually quite straightforward because we had the k-means centroid objective. So the k-means centroid objective was this objective which introduced the concept of centroids, and here we just use the formulation of minimizing the distance of all points to their centroid by means of the cluster indicator matrix Y. And then you see that if we want to minimize here this sum, then we can have for every index I here only one index S for which YIS is equal to 1, and for all others it's equal to 0. So then which S do we choose? Well, then if we want to minimize, we choose of course the S for which this value here is the smallest one. So we choose the cluster whose centroid is closest to our data point DI. Okay, so as a consequence, we get now that Lloyd's algorithm actually performs block coordinate descent. This is also called alternating minimization. And the update rules are that X is updated as the minimizer of this objective when we fix our cluster indicator matrix Y to the one we had in the previous step, and then Y, the cluster indicator matrix, is updated as the minimizer of the objective when we fix X to the previously computed matrix of centroids. And then we have again these two steps which we actually before derived just as a heuristic, as a method which made sense to us. And now we have it that we can also derive some guarantees for this under the framework of block coordinate descent. So in coordinate descent we update it subject to every coordinate, and here in block coordinate descent we gather all the coordinates which in X and then update them, and we gather all the coordinates which are in Y and then update them. And similar to what we have said for coordinate descent, we also know that the sequence of all iterates converges since we decrease the objective function value in every step. So the residual sum of squares of the initialization is larger than the residual squares of the first iteration, and so on and so on and so on. And it's bounded below by 0, so it has to converge. So at some point the algorithm cannot improve the solution any further. Okay, so that means now that our method, which we derived, Lloyd's algorithm, is actually also theoretically founded by the framework of block coordinate descent and the properties like convergence, for example. But with k-means we do not get the global minimum, and hence we do have some issues to deal with. Well, first of all, the k-means problem is NP hard to solve, and in contrast, the truncated SVD, the rank R matrix factorization problem, is polynomial solvable. So there's quite the big gap between the complexity of these two problems, although they are both instances of the rank R matrix factorization problem. And yeah, k-means poses a non-convex optimization problem, and every feasible cluster indicator matrix and the corresponding centroids are a local minimum. And that is because it is a discrete optimization problem. So if you, for example, have a discrete optimization problem which optimizes over integers, then, for example, consider here these integers as the points in the feasible set. And let's say that we have a function value for all of these feasible sets, which is here indicated by the cross. Now you could say that, for example, maybe this here is a local minimum, and this is a local minimum, and maybe also this is a local minimum. Because what you might do is you say like, okay, probably this goes like this here, right? And then we have here these local minimas, but actually all of the points are local minimas, because if you go a bit to the right or a bit to the left, then you're outside of the feasible set. So that means that you cannot go a bit to the right or a bit to the left and decrease your function value. And hence, according to the definition of a local minimum, we have here local minimas at all points. At the same time, these are all also local maximizers, so this is really confusing in a way, but that is just the nature of discrete optimization. And as a result, finding a good initialization is important, because we just get a local solution. We only know that we decrease the objective function value in every step, right? That we could derive by the framework of block coordinate descent, but we don't know how good the solution will be when it converges, right? So for these problems where we have a big set of local minimizers, which are all possible solutions to our problem, and for k-means we have actually quite good heuristics to deal with this problem, and we will then explore in the homework how to do that. Now, the most important slide of this lecture is given here. So why is it important? Because it summarizes in one result the whole story of k-means we have had in our lecture. So it says that the following objectives are equivalent. The first objective is the one which told us that we actually want to minimize the distance of the point to the corresponding centroid, and therewith we also developed the scheme of Lloyd's minimization by solving these subproblems. And the second objective is a formulation in the framework of rank or matrix factorization, and there we have now the objective to minimize subject to the cluster indicator matrices Y, where X is here given as the matrix returning the centroids column-wise. But then we have also seen that the centroids are actually the solution to the objective when we have given a matrix which indicates our clusters Y. And therewith we have here this more general formulation of our matrix factorization definition for k-means. And in this way these objectives reflect also the journey we had here in these lectures and how we answered the questions which arose subject to the k-means algorithm. And yeah, the big takeaway of this lecture is that the k-means algorithm, which is known as Lloyd's algorithm, performs block coordinate descent. So today we have seen this very hard to solve discrete optimization problem of k-means, and we also have discussed how to optimize this problem and put it into the framework of the methods we have seen before, like for example coordinate descent, and also other problems which we have discussed before, like the rank or matrix factorization problem. And what I wanted to show you now in the last part of this lecture is what that looks like in practice. And yeah, then let's go through the notebook in the upcoming